Welcome to class 4. We're going to continue on with the discussion of the generalized Lotka-Volterra model in the high diversity or high dimensional limit. That's the limit where the number of species S that you put in goes to infinity. We're going to go back and start off from the cavity solution that we derived yesterday using the cavity method. And then we'll go on to compute these key thermodynamic quantities that we said we wanted to compute yesterday. And in particular, they're going to be the diversity of the community, which is the fraction of the S species that you put in that eventually survive. We're going to talk about computing the abundance distribution of all of the species. And we're going to also care about the feasibility and stability of the fixed points that we have been talking about. Okay. And the key things that we're going to see, our goal is going to be able to understand and reproduce these two diagrams over here. And in some sense, this can be a visual summary of sort of the Lotka-Volterra model as a whole. The first is essentially something that summarizes these first three, this set of things, which is how diverse and what the abundance distribution is. What we will see is that the abundance distribution of a large number of species, when we put them in and run them according to the GIV model, is nothing but a truncated Gaussian. We already saw kind of hints of some kind of truncation going on yesterday when we were talking about max of 0 and something else. We already argued that something was a Gaussian random variable. So we'll kind of formalize that a little bit today, and we'll see that in the end, species abundances in any particular ecosystem that you look at are well described by a truncated Gaussian. And a truncated Gaussian has three properties. It's the mean, its variance, and where you truncate it, right? So this kind of like the equivalent of the 0th moment, except of course the 0th moment of any distribution is 1, the 0th moment modulo truncation, the first moment, and the second moment. So those are exactly the three numbers that we'll care about. The truncation point just tells us basically what fraction of the Gaussian is actually truncated. That's what fraction of species actually survive. And of course, the mean and the variance will tell us about the mean abundance and the variance in the abundance of the species. And for feasibility and stability, we'll care about this phase diagram over here, which we'll also derive today. And what we'll really see is that to get this phase diagram, you really need to focus on these two parameters of our ensemble that we were talking about yesterday, mu and sigma. And to remind you, mu was some S times the mean of interaction strengths, the mean of the AIJs. Remember, we had AIJs was some mu over S, right? So mu, that means, is S times the actual mean of the interaction strengths between species. And similarly, sigma is root S times the standard deviation, right? So just kind of remember that sigma is not the true standard deviation. Our true standard deviation was some sigma divided by some root S, which is just a system size scaling. Right? And if you look at this phase space of mu versus sigma, what you see is basically there are these two phase sort of boundaries separating and creating three phases. There's one phase in which you get a unique globally stable fixed point, which attracts all trajectories. That's often what's called the UFP phase. We'll see how to understand that. At some point, if you keep increasing sigma, you'll cross over generically into what's called a multiple attractor or chaotic phase. So often also called the MA phase in the literature. And then if you keep increasing sigma further, at some point you will cross over into another phase, which is called an unbounded growth phase. And this is really a phase in which the model is badly behaved because species abundances kind of start to diverge and sort of run away. We'll again see how to understand what happens here. And there's, of course, all this funny stuff happening over here on the left. And this is really a situation where the mean mu becomes large negative. And this also we'll see to understand, but this is really, again, a behavior of the Lotka-Volterra model where it's not very, very well behaved when a sufficiently large fraction of the interaction strengths become negative. And to remind you, negative negative interaction strengths is a situation where there are mutualistic interactions, right? So in this case, if you find pairs of species that are mutualistic, they promote each other's growth, you often find a situation in which the species will keep growing all the way to infinity. So this, in some sense, this UG phase or the unbounded growth phase, is in some sense a phase where this model is not really well behaved, right? And we'll see that we can understand these three phases in terms of just the behavior of the cavity solution. So we'll see that in the unique fixed point phase, that's characterized by the cavity solution being both feasible and stable. See again what we mean by that. At some point, this first phase boundary is also going to be an instability boundary, because this is the boundary across which the cavity solution remains feasible but becomes unstable to perturbations. And then finally, you'll cross over to another phase. So this phase boundary is also called the infeasibility phase boundary, because at this point, the cavity solution will generically cross over to become infeasible. And of course, when it's infeasible, there's no sense in talking about its stability, right? So there's really feasible plus stable, feasible plus unstable, and then an infeasible phase. These are really the only three phases you could expect given the qualitative behavior. Okay, and so today we're going to spend our time sort of deriving and thinking about all of this. I'm not going to be, and so remember in our calculation today and yesterday, we've only been talking about fixed points and the behavior of fixed points. And so really what we will do is we'll start off from this phase and ask when things break down. And I won't really describe the behavior or how to describe the dynamics in this chaotic multiple attractor phase, because of course, there you don't have any steady state behavior. So we'll spend some time tomorrow talking about how to analyze the dynamics in that phase. Okay, so that's the plan for today and tomorrow. Let's get started. What about rho? Great question. So this phase diagram that I've drawn is for a particular value of rho. So this is rho fixed. What you will see, and we'll talk about it later in this class, is that the qualitative behavior of this phase diagram remains the same for any value of rho that you fix. The only thing that changes with rho is basically whether this instability boundary moves up or down. Okay, and also whether this infeasibility boundary kind of twists a bit. But the fact that there are three phases, the fact that they are ordered in this way, that does not change. So rho just kind of changes the transition points and exactly how bendy the phase boundaries are. So we'll see when we derive equations for these phase boundaries that rho shows up there. Okay, all right. So we have a lot to do. So let's get started. So all the conceptual stuff is really present in this cavity solution that we kind of derived yesterday. So to remind you, we started off with a system of size S. We added a cavity species with abundance N0. That cavity species disturbed the old system, which was at steady state, and we were interested in computing what happens in the new steady state. We argued that the other species that existed before the cavity species just experience a small perturbation. So their changes in abundance we can describe in terms of linear response. So really the key quantity that we wanted to compute was the abundance of this cavity species. So that's the key equation that we derived yesterday, which was in terms of this max of 0, comma, K0 minus this guy over here, and then this guy, this double sum over here. Yeah, this is really the key equation from which we will extract all of this. Okay, so somehow this contains all of this kind of behavior. We just maybe can't see it right now. So we also argued yesterday that once we substitute our ensemble, which is what we were working with yesterday, we could show that to leading order, this is just a number, which is sigma square rho nu. To remind you, sigma is just this parameter that describes our ensemble. Rho is a parameter that describes our ensemble. What was new? New was an unknown we introduced, right? So this had to do with the susceptibility matrix. And new was basically the mean value of the trace of the susceptibility matrix. The mean value of the diagonal entries of this susceptibility matrix, right? So you can also think of it as the trace of susceptibility matrix divided by S. Of course, in an infinitely large matrix, the trace is going to blow up. So, but the trace over system size, you expect to be a finite quantity, right? So that's a number, right? That's a number. When I say trace of nu here, I really mean this is a matrix, right? So we introduced this entire susceptibility matrix when we used our linear response assumption. But in the end, what we kind of discovered was that the only way this matrix matters is through this one number, right? And this is an unknown. So we don't know what it is. We need to determine it. We were also arguing yesterday, and this is where we kind of left off, that this should be a Gaussian random field. And what was the argument there? Right, this is almost a guess at this point, right? The kind of argument that we are trying to make is that, look, this is a sum of many, many random variables. The components of each of these random variables are like A0, J, and Nj without zero. Nj without zero is the abundance of species J before you perturb anything. And J0 is how this species affects the cavity species. Both of them you expect to be uncorrelated. And this is a sum over sort of many, many things, right? So this is like A01, N1 without zero, plus A02, N2 without zero, plus A03, N3 without zero, and so on and so forth. And if N1 without zero, N2 without zero, N3 without zero, all of these abundances of different species are weakly correlated or uncorrelated with each other, then you would expect that these are IID random variables. And so you should be able to use the central limit theorem and argue that this should be a Gaussian random field, right? And if this is a Gaussian random field, then you should be able to derive its moments by the uncorrelated nature of A0J and NJ0 that we wrote down, right? So how do we do it? Let's just quickly do out that part. So we're conjecturing, or we have an ansatz that this thing over here, call it 1, is Gaussian. And if it's Gaussian, I should be able to write it down, this whole thing down as a Gaussian random variable, right? Which just means I need its mean and I need the standard deviation of this variable, and I can just replace it then with a new Gaussian random variable. And so we can try and compute this, right? So again, we can substitute our ensemble. A0J will be mu over S plus sigma times A0J. If I sum that over with Nj0, Nj without zero, I will get this, right? What is this guy over here? This is Nj without, this is N1 without zero plus N2 without zero plus N3 without zero, blah, 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 divided by S. Have we heard of a quantity like that ever in our lives, where you sum up a bunch of things and you divide by how? It's just the mean abundance, right? It's just the mean abundance of species. So whatever species abundance distribution I'm looking at, this is just the mean of that, right? So I can also write this down. There's a minus sign here. So I can also write it down as mu minus mu times mean of n minus sigma times this A0j and j without 0. Right? So that's a constant. Remember, this again, do I know this? I don't, right? I don't know the mean abundance. That's kind of one of the things that we want to compute. So whatever unknowns I'm finding along the way, I'm just going to put a little box around them to remind me that these are all unknowns that in the end we'll have to compute in some way, right? And we're making ansatses and guesses along the way. In the end, everything will need to be self-consistent. So we'll need to verify that. Okay, so this is some Gaussian random variable. This is some A0j, which is like a fluctuation. So how will we get the mean of this? What will be the mean of this Gaussian random variable? That'll be the mean of this plus the mean of that, right? What's the mean of this? It's just this number. And what's the mean of this guy? If this and this are uncorrelated, which we argued they should be, because this one is before the perturbation, this one is after the perturbation, they shouldn't know anything about each other, then what should this whole term be? 0, right? So that means I know that this thing has a mean which is minus mu times mean of n. I still don't know what this guy is, but if I knew it, then I would know the mean. And I can also compute the variance, right? Or I can at least compute the second moment. And the second moment would, of course, then depend on this guy, right? The square of this. I have to square it and take the average. That would depend on A0, the mean of A0j squared, which is what? 1 over S, and then some mean of nj without 0 squared, right? So this will involve 1 over S, sigma. I try to compute the second moment. There'll be a sigma squared, there'll be a 1 over S, and then there'll be a sum of nj without 0 squared, right? What's this quantity? That's the second moment of the abundances, right? This is again a thing I don't know, right? This is one of the things I'm trying to find. This is also an unknown. Yeah? Which one is diversity? No, it's not diversity. So remember what is n? It's the abundance of a species, right? So strictly speaking, this is like, think of this as mean of ni, right? There are all these different abundances of species. This is the mean abundance. The mean abundance has nothing to do with diversity, right? Yeah. But I had S species to begin with, right? That was my assumption, right? When I started off with the cavity method, I had S species at steady state that were all surviving, right? That, I mean, if you're saying that S is the diversity, that's kind of already given to me. What I need in the end is S star over S, right? This is not diversity, it's the mean abundance. We haven't talked about diversity yet, right? So we have the mean of this variable, and you can also now compute the standard deviation of this variable. And what you'll find is, I mean, if I went over this a little bit fast, is mostly because it's just algebra. You all know how to compute this, and I want to complete a bunch of things. But basically, what you'll see is that this should just be sigma squared mean of n squared. Okay, so now I can just basically substitute all of this and write down my same equation for n0 in just a slightly different way. This is ensemble independent, as we argued yesterday. This is just a feature of this GLV model. What I'm going to write down now is an ensemble dependent version. Right? This is going to be n0 max of 0, comma, k plus sigma k, some zk, minus mu mean n, minus sigma mean of n square. Yeah, zn. Okay, is everyone okay with this? Could also be a plus. Okay, it's just to remind you, these zn's are just standard normal variables. Mean 0, variance 1, right? That's just how you write any Gaussian random variable. You write it down as a mean plus a standard deviation times a Gaussian random variable, right? So then when you do that, so I did write k not like that, right? I wrote it down as a mean k plus a sigma k times some zk, right? Zk is again some other Gaussian, some other standard normal variable, right? So that was my ensemble for k. That was what I assumed for k, right? K is the mean k. This is just the standard deviation times some random number, right? That's a constant. That's a constant. That's a Gaussian random variable. That's a Gaussian random variable. What's the sum of two Gaussian random variables? Another Gaussian random variables. What's the mean? What's going to be the mean of that Gaussian random variable? 0, right? This is mean 0. This is mean 0. Mean will be 0, and what will be the standard deviation? You sum up the variances and you take the square root of that, right? That's the variances add up. So that will be root of sigma k squared plus sigma squared mean n squared, right? So another way of sort of writing this down would be k minus mu mean n plus root of sigma k squared plus sigma squared mean n squared times some other z, right? This is some other Gaussian random, this is some other standard normal variable. You're confused about the statement that I just made about sum of two Gaussian random variables being Gaussian random, then either come to me later or look it up. The only thing that we've done is that we've massaged this equation that we had yesterday, which was ensemble independent, and converted it into an ensemble dependent equation. K0 is Gaussian, right? That's what we did yesterday, the first 5 minutes, right? We had an ensemble where all the Ks were Gaussian. And of course, our cavity species is statistically identical to all the other species in the ensemble, right? Which means that it also, K0 is pulled from the same distribution, with the same mean and the same variance, right? So here I'm just exploiting the fact that the cavity species is statistically identical to all. Okay, everyone's fine with me sort of writing it in this way? Okay, so if you're okay with this, then actually you can immediately see maybe point 3 that's sort of written over there in our summary, which is that if you care about P of N0, then that should be a truncated Gaussian. Can someone tell me why? This orange box will tell you that it should be that. Okay, so you're talking about the max part first. So that you want to talk about the truncation first? Maybe let's talk about the Gaussianity first. Yeah, so let's say we forget this max bit. If N0 was just this, what would be the distribution of N0 of the abundance of this cavity species? Gaussian, right? Why? Because that's just a constant, right? That's just like the mean. That's this part. This gives you the standard deviation of that Gaussian, right? This is just a Gaussian random variable. So this bit is just saying that n0 is a Gaussian random variable with a mean k minus mu n over 1 minus sigma square rho nu, and a variance sigma k squared plus sigma squared mean of n squared over 1 minus sigma squared rho nu whole squared. Right? And this entire Gaussian, if I were to draw a distribution of n0, that's what we're talking about, right? The mean is k minus mu mean n over 1 minus sigma square rho nu, right? Forget about the fact that I don't know what the values of some of these constants are. They are constants, right? So this will be some value, we just don't know what it will be yet, right? And there'll be some variance of this Gaussian, and that will be variance will be sigma k squared plus sigma squared mean of n squared over 1 minus sigma squared rho nu squared. Okay, and now we can talk about this max, right? What is this max doing? It's saying take everywhere that this Gaussian gives you something negative and do what? Just condense all of this and throw it all at 0. Right? Just kind of condense all of this and throw it all to 0. This is nothing but a truncation. Right? You're truncating this distribution, so everything to the left of 0 will pile up and sit at 0. Sit exactly at 0. So those will all be cases or realizations where you put in the cavity species, and what happened to it? It went extinct. Right? Because what is this distribution really saying? Right? What does it mean to have P of n0? It means you start off with the system with S species, you put in a cavity species, you ask what its abundance is, you do it again, and 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 you plot a histogram. This is that histogram, right? So in different realizations for different cavity species that are all have these statistics that are the same as the ensemble, you're going to get this distribution of abundances, right? And what does that mean? There'll be some fraction of times that this cavity species will go extinct, right? What is all of that fraction? It's just whatever fraction of the area under the curve is negative, right? The more and more this Gaussian shifts left, the more and more you get a fraction that's on the negative side, the more fraction of times that the cavity species goes extinct. On the other hand, the more and more you stretch out this Gaussian, again, the more and more things get truncated, the more and more fraction of times this cavity species goes extinct, right? So there are really three things about this distribution that we will then care about, right? One is just what we will call now phi or phi n, right? This is the fraction of times, this is the fraction of the distribution that's truncated. Then, of course, we'll care about, since this is a Gaussian, just the first two moments. These three numbers fully describe this distribution. Any questions about this? Yeah, exactly. So you'll just normalize it with respect to the surviving part. Of course, you just do it so that the 0th moment is still 1, right? The diversity will be whatever fraction of this mass you truncated. Oh, sorry, 1 minus the whatever fraction of this mass that you truncated. Okay, the last step that's left, which was the last step in the cavity method that I wrote down yesterday, is just to say, hey, look, we derived everything right now for the statistics of the cavity species. Our goal was to derive something about the statistics of all the species, right? The only thing that you need to do is to realize that this cavity species is nothing but any other species, right? And a system is large enough, you put in anything, every species is statistically the cavity species, right? So all we need to invoke now is just that P of n0 will be basically the same as any P of Ni, right? In other words, we can invoke self-averaging. Another way of saying this is that, this is the thing that you probably heard of in other areas of statistical physics. You can take a really large system and you can look at the abundance distribution of all the species in that system. That should be this distribution, the truncated version. You can also look at one species across many, many ecosystems with different realizations of this kind of disorder, and you'll also observe the same distribution of the abundances of that species, right? So you can kind of focus on one species across many ecosystems, or you can focus on many species in one ecosystem. You get the same distribution, right? This is, like I said, an ansatz, right? This is a guess that we made based on a few assumptions that we had made along the way, right? We focused only on the leading order contributions from all of these things. We focused on the fact that N1 without 0, N2 without 0, and 3 without 0 probably are not correlated or weakly correlated, so that we can apply the central limit theorem and think of this as a Gaussian random field. But in the end, you get an answer, you need to check it, right? And so what you can do, how do you check it? How do you check if our ansatz works? Why should you match with experimental data? Does the experimental data have to follow the generalized Lotka-Volterra model? I mean, if it doesn't match, will you say that something about your ansatz failed or something about your conceptual model failed? You wouldn't know the difference, right? Do you do something simpler? If I told you none of this theory, none of the cavity method, I just told you the generalized Lotka-Volterra model. Exactly, right? So what's the first thing that you would do? The answer is not theory. The answer is not trying to do some sort of analytics, right? The answer is always you try to simulate these equations, you try to simulate the dynamics, and try to get a feeling for what the answer is, right? You try to guess the answer, right? But you should know what the answer ought to be, right? And there's a very easy way to get this answer. There's a very easy way to get a sense of what this distribution should look like. Just do a damn simulation, okay? If you do a damn simulation with you won't be able to do it with infinitely many species. Do it with 100 species, do it with 200 species, do it with 1,000 species, whatever your computer can handle. And just plot a distribution of the species abundances at steady state. And what you will find, I'll keep erasing this now, not to confuse you, is basically, now you'll be drawing some sort of histogram from your simulations of what the abundance distribution looks like. And basically what you'll see is that it matches really well. Okay? Modulo some unknowns that we don't know right now, right? So let's just figure out what are all the unknowns that we left behind, because to plot this histogram, I've assumed that I know what this guy is, what the value of this is. I've assumed that I know what the value of this is. I've assumed that I know what the value of this is, right? We don't know what any of these are. And I've assumed that I know what this phi is. I don't know any of these right now. So we need to figure out a way of self-consistently deriving these numbers, and then we'll be able to actually draw this Gaussian out, right? Right now, all you can do with a check numerically is actually see if from your simulations you see a distribution that seems to look like a truncated Gaussian, right? That's all you can do, but you can't do a quantitative match yet. Okay, so let's try to see how is it that we then self-consistently derive all these unknowns. Okay, but the form of the distribution you can already check. If that bit is not clear, please ask me now, because this idea goes beyond Lotka-Volterra model or ecology or any of this. This is just a standard idea in statistical physics. It's a statistical physics school after all, right? Okay, maybe you'll see it in action. Okay, so what we are trying to find out, let me just write down what all we're trying to find out. We're trying to find out this number nu. We're trying to find out the properties of these abundance distributions. There are 4 unknowns that we have. So how many equations are we looking for in the end? 4, right? Right now we have 1, right? So we'll do something that you might say, what are you doing? But really what we're trying to do is massage out 4 equations out of this box thing, okay? Using this ansatz that we came up with, which is that of a truncated Gaussian. And using this idea of self-averaging, which again, we don't know if that's true. We're going to invoke it. And if things work, then things will match well. If it doesn't work, then self-averaging would have broken down and we will be left in the water, and we'll see what to do in that case tomorrow. Yeah, but today everything will indeed work out. So let's think about nu. Nu, remember, was what? It was 1 over s times the sum of nu I, where I goes from 1 to s. So this means I have to go and look at the abundances of all, and the abundances of all species, right? Let's also remind ourselves what the definition of this nu was. What was the definition of nu I or nu ij? Del ni, del ki, right? So this will be del ni, del ki, sum from 1 to s. This requires me to know an expression for ni, right? I don't know it. What do I know an expression of? N0, right? And so what we're going to do is that we're going to just replace this with del N0, del K0 going S times. Okay, this is like, in some sense, what we're trying to do is we're trying to ask what's the average value of del N0 by del K0. Right? That's essentially what we're trying to compute. It doesn't have to be this way. Like I said here, what we was assumed is that the statistics of N0 is the statistics of every other species. Okay? And I'm doing this because this is something I can write down. Right? How do I get this? Everyone knows how to take a partial derivative, right? So I have an expression for N0. You can take a partial derivative with respect to K0, in which case I should just get rid of this K plus sigma K. Just think about my K0 over there. And what would I end up getting? Because really this is a random variable, right? So we want kind of the expected value of this thing. And this is a self-averaging quantity, so its expected value will be its actual value. Right? This without this thing is going to be a random variable, right? Yeah, so what's the partial derivative, guys? Everyone's confused about how to take a partial derivative? 1 by 1 minus, okay. Is there everything okay with this, or have people conveniently skipped over some important letters in this expression? How would I think about, you've just taken a partial derivative of this, right? But will this quantity, when you take a partial derivative, always give you this number? No, right? It'll only give you this number, some fraction of times, right? What's that fraction? Phi, right? A fraction 1 minus phi times, it'll give you what? 0. In which case, what will be the derivative? 0, right? So strictly speaking, This is phi n over 1 minus sigma square rho nu plus 1 minus phi n times 0. Right? That, of course, is 0. Is that clear? There's an argument you have to keep in mind again and again. It's coming up because there's a max over here. Right? Only some fraction of times is n0 actually going to be given by this quantity. Okay? So nu, we have an equation in terms of nu and phi n. Of course, this is something that we can't immediately compute yet, but the hope is we'll get a bunch of coupled equations in the same coupled unknowns, which then we can solve. So now let's think about phi n. And phi n is what? Phi n is in some sense is S star over S, right? In some sense, the fraction of cases in which this cavity species survives, or in any system with S species, what fraction of that S survive. And so in that sense, that's 1 over S times sigma of some theta of Ni, where I goes from 1 to S, right? This theta function is just saying it's 0 if Ni is less than 0, it's 1 if Ni is greater than 0. And so you're just literally counting. This is diversity. This is how diversity is different from abundance, right? Diversity is you count something if it's present, you count again if something else is present, if something is absent, you don't count it, right? So this is the 1 over S. This is going to give you S star. And of course, again, I'm going to use the same trick as I used there before. I don't know anything about Ni. I know stuff about N0. So I'm just going to use the same statistics. So in some sense, this is going to involve this integral. It's an integral. Okay, let's just do all of the others as well. I want mean of n. It's getting a little bit tiring now, but 1 over S, sum over n, I without 0, I goes from 1 to S. That's just the definition of the mean. And I, again, won't care about this. I care about just invoking it in terms of n0. And that's just this guy, this other integral. Right? This is all piece of cake for you. You guys did this in your prep school and everything else that you've ever seen before. So I'll go through this fast. You can also do it for n squared. And in some sense, that's it, right? We haven't talked about these integrals yet, but these are 4 equations in 4 unknowns, right? And do you see that these equations also involve all of the unknowns? Because they involve all of them through this P of n0, right? Which is going to be given by that truncated Gaussian, right? So in some sense, all of these 3 equations are about moments of truncated Gaussians, right? It's like the 0th moment. This is the first moment. This is the second moment, but post-truncation moment, right? Not the moment of the untruncated distribution. Okay. So what we need, just to sort of wrap this off, is some mathematical identities of moments of truncated Gaussians. And this is either a thing that you know, or you look up Wikipedia, you get some identities for these moments of truncated Gaussians. So I'm just going to tell you what that looks like. But before that, maybe I'll take a question. Yeah. If you integrate from minus infinity to infinity, right? You're integrating from 0 to infinity, right? The limits of the integral are important, right? That's how we're respecting the truncation. Yeah. Yeah. Meaning that if you just look at the 0 plus part, that is not normalized, right? If you look at the part with the 0, it is normalized. So strictly speaking, what we are really doing here is this limit is actually 0 plus. These are all 0 plus, right? Because you're only looking at the abundances of species that survive. That's what gives you the mean abundance. That's the bit that you're really missing out. And that's why it's not normalized, and that's why this is actually not 1, right? But some number less than 1. Great clarification. Okay, all right. So let's just finish this off. So, I mean, like this is just going to be some math identity, but maybe let's quickly brush up our Gaussian integrals. There's really very few Gaussian integrals in the world that we can do exactly, right? Which are those? Does everyone know what a Gaussian integral is? Can you do e to the minus x squared dx integrated from minus infinity to infinity? Okay, is that a Gaussian integral? Okay, what's the answer? Yeah, something that depends on pi, right? Can you do that same thing from 0 to infinity? Yeah, it's symmetric, right? Can you do it from a to infinity, where a is not 0? You guys heard of a function that then you use if then you can't actually write down a closed form for this? Yeah, exactly. You write down error functions or complementary error functions, right? Those are functions that sort of encapsulate some complicated looking integral that we don't know how to do, but we can do numerical, right? Numerically, of course, you can integrate a Gaussian however you want, right? So in the end, this is a truncated, this is some sort of Gaussian that we are not integrating in some nice way, right? We are not integrating it about its mean. So we're not going to get something nice. We're going to get something that's ultimately in terms of error functions or some derivatives of error functions, right? So that's really what I'm going to write down here. Okay, so there's really no mystery. So you can use this identity or way of sort of writing down the jth moment of a variable y, of a random variable y, which is a truncated Gaussian, which is sort of this way. That's just what the jth moment is. So what I'm assuming in life is that this y is a Gaussian with mean C over B and standard deviation A over B. No, the other way around. A over B, standard deviation C over B. And I'm truncating it at minus A over C. And what's the jth moment? Right? That's just really what that integral would be. And so really you can write this down as C over B to the J times some function which we'll call W or omega, however you want to call it, some Wj with an argument A over C, where Wj we'll define to be of A over C, we'll define to be the following integral. This is just some algebraic manipulation, nothing kind of fancy here. Just to tell you that this means that y is going to be something like max of 0 and C over B, Z plus A over B. So you again have something truncated at 0 with some mean A over B, variance C square over B square. In that case, you can all kind of relate it in terms of these W functions, and you can also write down these W functions in terms of error functions. And I'll leave it as an exercise or a homework for you to express this function or that integral in terms of error functions. And so for us, really we have a situation where B is 1 minus sigma square rho nu, A is K minus mu mean N, and C is sigma K squared plus sigma squared mean N squared. And so you can also write this down by substituting that whole thing. This will be in terms of this evaluated at j equals 0. So just to write down a couple of them, give you a feeling. This will really be W0 A minus mu mean N of 1 minus sigma square rho nu. This one will be sigma K square plus sigma square mean N square over 1 minus rho sigma square nu times W1 A minus mu mean N. Same argument. And you can also then figure out this one will be this guy squared times W2 times this guy. Right? So I'll leave it to you to write down. What do we do with these four equations? Yeah, maybe I will write it down while you guys think about that. How do we proceed? We want to solve for all the unknowns on the left-hand side, right? These are all coupled equations in terms of our four unknowns, right? Now you can kind of clearly see this guy involves nu, mean N squared, mean N, all of these guys involve some versions of these, right? So these are our four equations in our four unknowns that we were looking for. They should have a unique solution, hopefully, or they should have at least one solution, right? How do we find it? Does anyone know how to solve four equations and four unknowns? Three equations and three unknowns? Two equations? Sorry? Maybe I heard someone saying linear equation. So does no one know how to solve four non-linear equations and four unknowns? Numerically, right? Yeah. How do you solve sine x minus x equals 0? Right? Numerically, I mean, of course, x equal to 0 you can get by inspection, right? So yeah, these are four equations and four unknowns which you can solve numerically. Again, I'm not going to do it in class, of course, for lack of time. But again, if you've never solved these kinds of equations numerically, it's a fun exercise, right? But let's just recap what it is that it'll give us, right? If you put down these four equations in some nice solver on your computer and you give it all your parameters, sigma, mu, sigma k, rho, and so on, it'll spit out four numbers, right? One for each of these. What can you do with those four numbers? You can now predict and make this truncated Gaussian, right? Because now you know every number that goes into these Gaussians. So you can predict exactly what this truncated Gaussian should look like. In other words, you can draw this guy over here. You can get these bars from numerics, and now you can actually match what you see from simulations exactly with what you get from this cavity theory, right? And if all of our ansatses and our assumptions and our approximations of linear response, et cetera, were all fine, remember we made lots of them along the way, it's had no reason to match, right? I just want to make that clear, right? Just because you've done a bunch of maths over 2 days doesn't mean that in the end that orange distribution needs to match this histogram over here. Yeah? But if it matches in any situation, that means in that particular, for that particular set of parameters, everything was self-consistent and fine, right? If it doesn't match, what do? Something broke down, right? Something along the way broke down. One of the assumptions or many of the assumptions were not valid anymore, right? There might be the self-averaging assumption, which is what we use sort of all along the way here, that might break down. There might be some assumption of ignoring sub-leading terms that might not work. This is indeed what will fail when you try to do simulations for 2, 3, or 4 species and try to match it with the cavity solution, right? That you will not expect to work, right? Other things that might fail, there might be some other structure that makes all the ends a little bit correlated with each other. That might break the Gaussianity assumption, right? So there are many, many ways in which various things that we've assumed throughout the calculation might fail, right? And so there's no reason this has to work. If it does, you should be happy, right? And there are cases in which it does work, okay? And that's exactly what this entire phase is, okay? So what we'll do in the next 35 minutes of this class is try to see how we can, again, look at this solution and predict where the solution ought to work, where the solution ought to fail. Okay, and these equations contain the answer to that question. Okay, so let's see that. Okay, so thus far what we have, if we can solve this, do we know about diversity and structure? We do, right? Because essentially we know phi n. So now we know what fraction of species we expect to survive. And indeed, we would have checked it with numerics, that that is indeed the fraction of species that survives. And we would also know something about the structure, right? Of the species that survive, what's the mean abundance, what's the variance in abundance, what does the distribution look like? It looks like a Gaussian, at least a truncated version of it. And so that those first two things we have now. What is left and what we don't know is whether the solution that we derived, which was a fixed point, is feasible or stable, right? Remember, this value over here could be sufficiently negative that this Gaussian moves all the way to the left, right? And then at that point, you might not have a situation in which anyone survives, right? So we'll talk about now how to think about feasibility and stability for this model. Okay, and so really what it will boil down to is asking the question about this box solution. The feasibility question will be asking when this box solution is actually physically relevant solution that doesn't blow up. And the stability solution, the sort of stability question will be about what? It'll be about perturbing away from the fixed point and asking for the response of the system. If that response is so that the system runs away from this fixed point, it'll be unstable. If it comes back, it'll be stable. Okay? And so we'll again exploit this cavity solution to get both of those answers. Any questions about what we've done so far? I'm going to leave this guy behind because we're going to use it. Maybe I'm also done. Okay, so let's first talk about feasibility. I want to erase this. So what was the idea of feasibility? As a situation in which the abundances are all well-defined numbers that are non-negative and finite, right? Will this solution always give you something that's finite? Can you see a problem that might occur at some point? Can this blow up? When can this blow up? When this denominator goes to 0, right? There could be some particular value of nu at which n0 blows up, right? If that happens, the system would not be feasible, right? So it's really, this nu is a self-organized quantity, right? Sigma is something that we choose, rho is something that we choose, nu is something the system decides, right? How susceptible it is to perturbations, right? So there's really something about this nu that will help us figure out whether the system is feasible or not. Let's ask ourselves more about this nu. So remember, we sort of derived over there on the right self-consistent equation for nu. What kind of equation is this in nu? It's a quadratic equation, right? So all of us know how to solve a quadratic equation for nu. You can solve it and tell me that you'll get an answer that looks something like this. I did this yesterday when I was a little bit sleepy, so I could have had it wrong. It's a quadratic equation, right? Nu is what? Nu is some number, right, that tells you about the mean response of the system. And really, let's talk about what it physically means as well. It means if I perturb the carrying capacity of the cavity species a little bit, how much does its abundance change on average, right? That's really what this number says. And what should we expect the sign of this number to be? Should be expected to be positive or negative? If I increase the carrying capacity a little bit of the species, do I expect its abundance to go up or down? Ready? 3, 2, 1. Okay. 75% of the class does not want to say anymore because everyone's either terribly lost or confused. I'll repeat the question. Nu is just this guy, right? This is the expected value of the change in the abundance of the cavity species when you increase its carrying capacity by a little bit. So if you increase the carrying capacity of the species, do you expect its abundance to go up or to go down? You expect its growth rate to go up. And so you naturally expect it to grow a little bit more and have a larger abundance. So you expect it to be a positive number. Do you expect it to be a complex number? The change in abundance, right? Abundance are real numbers. Is at some point, this shows us the possibility that nu can become a complex number? Right? So this phi n kind of has a limit, right? There's a critical phi n, which is what? 1/4 sigma square rho. And really, phi n should be less than or equal to this number. That's a parameter that we chose. That's a parameter that we chose, right? And so what is this saying physically? One way to interpret it is that once you choose some variance of the interaction strengths and some amount of symmetry in this matrix, once you fix this matrix, can you pack as many species as you want? Well, not always, right? In the sense that, of course, when sigma is very small, this bound can be greater than 1. right? But this phi n can never be greater than 1, right? So depending on what the value of sigma and rho is, there may or may not be the ability for you to fully pack the system, right? By fully pack the system, I mean you put in a species and all has survived, right? But there are situations, especially imagine what happens as you make sigma larger and larger and larger. What is that doing? It's making the interactions between species more and more and more different. If you do that, then there can be a point where you can pack the system up to some number, let's say 0.5 or 0.6, but then pack it no more, right? Because what will happen if you pack the system at this critical packing ratio, and you try to add one more species, the susceptibility will become garbage. The abundances will blow up, right? You'll get something that's not well defined, right? Notice that that's only there's one way to avoid this. Again, what is that? You make rho 0, right? If you make rho 0, this is not a bound anymore that's relevant, right? So depending on whether this matrix is symmetric or somewhat symmetric or not symmetric at all or something else, there's going to be a bound on how much you can pack, right? That's one effect of rho, right? But really, generally, you can make a boundary, which you can call the infeasibility boundary, by essentially sketching out this curve over on this mu sigma plane for a fixed rho. Yeah, so you fix a rho. Every time you choose a bunch of parameters, or you choose a value of mu and so on and so forth, you can find a value of sigma at which this inequality becomes a strict equality. And you can do that over several values of your mu. And every time you'll find a critical sigma. That's exactly how you can get this boundary over here, right? So again, because you need to solve for this phi and nu, etc., numerically, this infeasibility boundary will also have to be determined numerically. But remember, not from simulations, right? Just from numerically solving this equation. If you actually try to derive it using simulations, yeah, you can talk to my students. It can take you weeks to do it because these simulations will become slower and slower and slower and slower the larger and larger number of species you have. So actually, figuring out what this boundary should be from simulations is going to be a terrible task. Okay, but this will be very fast. Clear how we get an idea of infeasibility and how we plot this infeasibility boundary? Yeah? Okay, so now that we've talked about infeasibility, let's talk about stability. And it's really going to be arguments of this type. Let me keep this guy. So what's the idea of stability? The idea of feasibility was you ask what happens to the abundances, are they well defined or not? And are they finite, are they non-negative? There's a situation in which they will not be finite. They'll blow up. The idea of stability is to start off at some fixed point, some cavity typical fixed point that you have, you perturb it, and then you ask for the response of the system, right? So really what we're going to want to do is you take some set of species ni, maybe ni without 0, and you add a small perturbation to sort of each of them. The way that we'll add a perturbation will be in the following way. There's some scale epsilon, which decides how small or large the sort of perturbation is. This nu I, this eta I is just a standard normal value, right? For some species, you add a little bit. For some species, you subtract a little bit. Some random perturbation. Right? This is a random perturbation. And then usually you say something about the Jacobian, blah, 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 blah. We'll take a slightly different approach, but conceptually the same, which is that we'll ask for the response of the system to the perturbations. That's also what you're doing, by the way, when you're computing a Jacobian, right? But here we'll do a statistical version. So what we'll care about is the following quantity. How much does N0 of all the surviving species change when we change a little bit epsilon, right? You go from epsilon 0 to epsilon not 0, right? So this is strictly speaking about epsilon equal to 0. But I'll erase that because it'll get tedious. And this will be a random variable, right? Because N0 is a random variable. So what we'll care about again are the moments of this random variable, right? So what we'll care about, we'll see, is that we'll first look at the first moment of this guy, then look at the second moment of this guy, and ask for whether there's any point at which we see something interesting going on. What should happen to the response? At some point, this response should either be finite, make you sort of come back, and maybe when there's instability, what you might expect is for this response to kind of blow up, right? And so what we'll see is actually this one will turn out to be boring. The first moment will turn out to be boring and uninformative. It won't tell us much about stability. Uninformative. This one is actually going to be the interesting one. And we're going to see that basically this quantity blowing up is what will give us a well-defined condition for instability setting in. And that's what will give us this instability boundary. Okay, so let's see that over the next few minutes. So what I need to do for any of this is, of course, I need to start taking partial derivatives of things. When I take partial derivatives of things, I need to know what the thing is of which I'm taking a partial derivative. And that thing is fortunately written nicely over here. I have my N0, which is max of this and that. N0 plus is just taking this part, right? It's just taking the part which is all the surviving species, because those are the ones that I am imagining perturbing. Why am I not imagining perturbing all of the other extinct species? Because I demanded an uninvasible fixed point, right? This is something we were talking about in the tutorial also yesterday. All the extinct species can anyway, if you put a little bit of them, cannot invade. We ensured that. And in fact, this max functions already assures us of that. So any instability that could occur can only occur because some of the surviving species can do crazy things once you perturb them away from the fixed point. So I have a different way of writing down this N0 plus. I'll just kill the max basically. Is this guy. It's K0 K minus mu mean N minus sigma little a0j nj without 0 plus minus sigma a0j epsilon eta j. Okay, all I've done here is I've taken the denominator over here. That's just my denominator over here. 1 minus sigma square rho nu. For the numerator, I've also assumed, by the way, just for simplicity, that sigma k equals 0. I think it'll be easier to work with that. I just don't want to keep carrying around a term which corresponds to sigma k. You'll see that it doesn't really change any of the qualitative behavior. Yeah. So I have k minus mu mean n. Remember, the mean of this quantity was mu mean n. And then I've just explicitly written down this guy as a random variable, mostly because I care about these n's. Right? These n's are what I'm going to perturb. Right? And so what I've also done is I've replaced nj without 0 with nj without 0 plus the perturbation that I perform. Everyone clear about this? Just some substitutions. Okay? And of course, I needed to do this because I want to take a partial derivative with respect to epsilon, right? So I need to put the epsilon in there, right? So I had something without this guy. Now I have something with this guy, and I want to ask what the first moment of this response is. Okay? So now I can just do some straightforward algebra. This is, of course, just a number. So it just stays out. And what happens here? Number goes away. This is just there's just a sigma that I'm going to send outside. A0j eta j minus sigma A0j dnj without 0 plus b epsilon. Okay, let's see if I did it correctly. Do I have all of my signs right? Sigma is outside, so that's fine. This guy is A0. There should be a plus here, right? Did I mess up something? No, that's okay. That's okay. That guy gives me A0j eta j. There's a minus sign here, right? Is this fine? Okay. And now, of course, I forgot one most important thing. I was taking the first moment, so I'll just take the first moment. Okay, so this first moment involves actually two things. I can look at them separately. Okay, can we argue really quickly that this should be 0? This A0j is a mean 0 Gaussian random variable. This guy was a mean 0 variance 1 Gaussian random variable. This is about a perturbation that I perform. This is about what the system was like before. They don't know anything about each other. So the mean of this is the mean of this times the mean of this. 0 times 0. That's going to go to 0. Similar argument to be made here. This will also be 0. This is 0. This is 0 always. And this is what I meant was by the first moment of this response is boring. It's just always 0. Some species go up, some species go down on average. But this is not going to be the case when I look at the second moment. So is everyone getting a feeling for this number that we're computing? We're computing the average response of the system to perturbations. And really what we are going to want to care about is we perturb every species. We ask it what happens on average to the response to this perturbation. Of course, we don't know about every other species, so we're going to assume self-averaging. And anything that involves what happens to species J, we'll replace with what we know happens to species 0. Yeah? And again, so we'll see that here. So here what I'm doing is I'm squaring and then taking the average. So that's just like I square this bit, I square this bit, I square this bit before I take the average. And so again, algebra notwithstanding, I'm going to get something of this type. We just have to be a little bit careful about when we take the order in which we do things. And then there's going to be a cross term from squaring this whole thing, right? This times that. So that's going to be twice sigma jk a0j a0k eta j d and k without 0 plus over d epsilon. Yeah, this one's not going to come with the square. Okay, clear? I mean, very simple. Squared this entire expression and then took the average. Right? So when you square this, I get this squared plus this squared minus 2 times this. Maybe there's actually a plus here. This squared plus this squared plus twice of this, right? So that's fine. This one you can kind of easily see, right? Mean zero, all uncorrelated. This one is going to go to 0. What about this guy? Is this going to go to 0 anymore? No, right? There are squares of things, right? So what is this going to give us? Again, let me carry forth the squares thing. This is going to be a sum over j, mean of a0j squared, mean of eta j squared, plus sum over j, mean of a0j squared, mean of d and j without 0, plus d epsilon squared. Okay, what do we know about this guy? This is 1 over s. What do we know about this guy? 1. And remember, there's one little tricky bit over here, which is that this is 1 over s, but this sum goes only over survivors, right? This is all happening for survivors. So there's a phi that comes outside this, right? So which is to say there's an s star that comes outside this. So this whole quantity becomes s star over s. Right? The 1 over s comes from this guy. The s star comes from the fact that you're summing over s star terms. That's phi n. What about this guy? Same thing. This is going to give us 1 over s. This is going to give us what? This is del nj without 0 plus over del epsilon, right? We don't know what del nj without 0 is. We're just going to imagine that that's exactly this quantity, right? So again, we invoke self-averaging. And we end up with the following. We end up with del n0 plus del epsilon squared average equals this whole thing times phi n plus phi n del n0 plus del epsilon squared average. Sorry about that terrible thing. This is phi n times this quantity squared, right? So this is like x equals something times phi n plus phi n times x, right? So this substitution came from self-averaging, right? It didn't mathematically again have to be the case. So if that's true, then you can actually solve for del n0 just by moving things around, left-hand side, right-hand side. You can actually solve this and end up with this. That's our key equation. Okay, all I did was some algebraic moving around. Right, this phi n comes outside, and now this is x equals constant times 1 plus x. You know how to solve that. We solve for x. That's this. That's exactly the quantity that we wanted. Right? This is not boring. Right? This is not 0 forever. In fact, this is going to be typically finite. So everything is going to be fine. All this is saying is that if you perturb the abundances by a little bit, then in the limit that that little bit goes to 0, you're going to have a finite response. Right? The abundances are going to change by some amount that's finite. Can this amount ever become infinite or undefined? It can, right? When this denominator goes to 0, the response can blow up, right? And what would that mean? That would mean instability, right? You're sitting at the cavity fixed point, which is what we assumed, right? You perturb all the abundances by a little bit, and you ask, there's a whole distribution of responses. What's the second moment of that? And that second moment blows up, right? That means at least some species are kind of just going crazy. Right? Some fraction of species are blowing up so that this response becomes undefined. Right? That's how the instability is setting in. Right? So this is a different way to see the same eigenvalue stuff that we were seeing in class 2. Right? This is just a statistical response way of seeing it. Okay, so now with this, we can actually get an instability condition. And that's really going to be when this guy goes to 0. And basically, you can massage all of these self-consistency equations, do substitutions for phi n, nu, etc., etc. And I'll leave it as homework. But what you can show, yeah, I would have done it if I had a little bit more time. But what you can show, can I erase this? Is that for any rho, there's a critical sigma at which this condition is satisfied, at which this instability condition is satisfied. That's just a little bit of algebra to get from this condition to what I'm just going to write down. If we use the self-consistency equations. But in the end, you end up getting a very, very simple form. You end up getting that these are the same thing. And to see this, you have to use the self-consistency equations that we wrote down, plus there's just this one simple property of those moments, which is that W2 of anything delta can be written down as W0 of delta plus delta times W1 of delta. This is just an identity that I'll leave for you to prove if you want. But just by basically substituting these 4 self-consistency equations and this mathematical identity, you can massage this condition into essentially that condition. This one, you can see now, does not depend on any of our unknowns. It's a much simpler condition, right? It doesn't involve phi, it doesn't involve nu, it doesn't involve mean n, it doesn't involve mean of n squared. This one did involve phi, right? This was really about packing. You can also think of this as being about packing, right? But this packing, like how much you can pack now depends on how susceptible the system is. Sorry? Yes, yeah. So this thing over here is root 2. Yeah, so in the end, you just get a very simple condition. There's a critical sigma, which is basically root 2 over critical sigma square, which is basically root 2 over 1 plus rho, at which instability sets in. Right? So there's a constant value of sigma at which instability will set in. And that's our instability boundary. So I didn't do the algebra. The algebra is quite simple. If you have trouble with it, come to me later. But this condition, I hope everyone followed. This just implies that. Okay? And when you do it, you can just plot the instability boundary as being some critical sigma. Right? So now you can just kind of see the full phase diagram of this model. Right? This is what we've been working up to for the past 2 days. For any fixed rho, you go over in mu and sigma. There's one region in which the cavity solution is both feasible and stable. There is neither of those conditions is quite satisfied. You're all good. And in this case, what you observe when you simulate things is that you get a unique stable fixed point to which all trajectories converge. I didn't tell you why there's this uniqueness. I won't have time to go through it. It involves some calculations about something called configurational entropy that maybe you'll learn about in the second week on disordered systems. But at some point, this cavity solution becomes unstable. And in this situation, you, of course, don't have a fixed point anymore. Right? It's still feasible, though. And then at some point, even this feasible but unstable solution simply becomes infeasible. There's also this little region over here that you might have noticed, where actually it's just possible to go from being feasible plus stable to just being unstable without ever, to just being infeasible without ever crossing over into instability. This over here, correct. It is a triple point. Yeah. At that point, the system is critically poised, right? You pack the system just enough. If you pack any more, you'll become feasible. Or if you just change something a little bit of the way, you'll also become unstable. Yeah? So what we've been doing so far is kind of assuming that we start off in this phase where things are feasible, stable, fixed points, and asking when that breaks down. What we'll work on tomorrow is how to think about the dynamics of the system once you're actually breaking this stability. Okay? In that case, if you actually, again, run the simulations and try to see what the answer is, what you see is that it's not that something terrible happens. It's not like all the abundances blow up. But what you start to see is some very, very interesting dynamics. You don't see that you put a bunch of S species, they'll do something over a transient, reach a fixed point, be stable and be happy forever. But instead, you start to see some crazy chaotic fluctuations where there are what are called boom and bust dynamics. There are some species that go up high in abundance, eventually come crashing down, and some other species go up high in abundance and come crashing down. And these kinds of chaotic dynamics continue forever and ever, right? Yeah. Good question. Where is mu equal to 0? This point over here is -1. So 0 is somewhere here. Okay, so in the interest of time, we'll end there. We figured out all of this stuff we wanted to figure out today. Tomorrow, we're going to spend some time in the beginning of the class, maybe the first hour, talking about describing this non-fixed point chaotic phase and understanding how to do similar analysis there. It'll turn out we'll have to do something called use something called dynamical mean field theory and write down some effective process that describes the sort of statistics of what's going on. And then in the last half an hour, I'll tell you a little bit about all the stuff we didn't do in this course that maybe will expose you a little bit to what's happening at the frontier of the field maybe nowadays. This is all stuff that we've been talking about up until today. The last two classes is stuff from 2016, 2017. Stuff I'll tell you tomorrow is from 2024. So you'll see that we're catching up pretty soon. And then I'll tell you just a little bit about what's going on nowadays. Okay, I'll see you guys tomorrow.